So our next topic is image restoration. Image restoration. The earlier topic that we saw was what was called image enhancement. Now this is very different from image enhancement. Okay, as you would have noticed, image enhancement was more subjective, right? There was a lot of subjective issues that we had. Okay, so it was more about enhancing contrast, illumination, compensation, and so on. Okay, somehow enhancing the visual appeal of an image. And as I said earlier, the visual appeal, some people may like, the same kind of visual appeal may not uniformly apply across people, right? Restoration, on the other hand, is very objective. Okay, objective, and and when we say restore, right, what we really mean is we would like to see an image F. Okay, but okay, this is like the latent or the ideal image. Okay, latent, original, whatever you want to call it, clean. Okay, it goes by various names, the clean image and so on. What you end up seeing is something G instead of F. What you actually end up seeing is G, and F has undergone some kind of a degradation. Okay, a degradation does not kind of necessarily always mean only noise or something. You could have various kinds of degradation, some of which I will list. If undergoes some kind of a degradation, it could also be a noise and a combination of other factors to give you G. And the idea is that what can you do in order to undo this kind of a degradation, undo objectively. By objectively, what we mean is we know we have a degradation model. That means we know the physics of degradation. We know the physics of degradation, and we would like to see, what we can do in order to undo this G so as to be able to get a solution that is close to F. Okay, F is what we are seeking. Now, you may not be able to get F, okay, which is why you may not always be able to get back your F. Therefore, typically you won't actually get back your F, but you will get something that is close to F. Okay, so we need a solution close to F. Okay, now this process by which F gets converted through some degradation into G is called the forward problem. Okay, and the process by which you take this observation G, which is actually a degraded observation, then you pass it through something, right? Whatever, some kind of a processing that will undo this degradation in order to give you back your solution, the original image. That is called the inverse problem. Okay, now forward problems are typically well posed. Okay, I'll talk about what we mean by well posed. Okay, so this is kind of straightforward. So here, right, all that you need is the image, and then somebody gives you a degradation and then says, right, use the physics of image formation, and then right, in order to be able to produce G. Now, inverse problem is like given G, okay, estimate, find F. Okay, so therefore, this is like you have an observation and you need to find it. Okay, this is typically an ill-posed problem. Okay, and we'll see what it actually means. This notion of ill-posedness is not something that is only limited to actually restoration domain or the image processing domain. This is something that occurs right across domains. It doesn't have to be just an electrical engineering kind of problem or something. It can occur right in any domain, and therefore most of the things that we will do will be kind of generic in nature. Okay, these are things that you could apply in various problems. Okay, and therefore you have a kind of a commonality across these problems, and therefore right, whatever solutions we have will also be kind of generic in nature. But then, of course, we will focus on some of those image processing problems that are interesting to solve within this kind of restoration framework. So the key thing that separates it from enhancement is this notion of objectivity. So it's more firmly grounded in the sense that we know exactly what we are asking, because we kind of believe that we understand what is the forward process, what is the degradation process, and we try to see, right, if we can undo the process. Okay, that really is the goal of the restoration. Okay, now there are various applications, right? So this kind of a restoration task, right, which is like solving an inverse problem, has applications in let's say various areas within image processing itself. For example, we have all seen See, for example, we have seen image blurring, right? Which is like a forward problem. Somebody gives you an original image which is clean and then says this is a point split function with which you should blur it, and then says you add some noise to it, you get your G. Okay, so when you have G is equal to HF plus N, that's like a forward problem. So we know how to actually do that. We have done it. We've done it for the space inverse, for the space variant case also. Now that is a forward problem. The inverse problem is what is called image deblurring, right? So in image deblurring, we just give you a blurred observation, and we will ask, right? Can you say restore the original focused image, right? So again, whether you have the knowledge of the point spread function or not, right? How much knowledge do you have of noise and all that, right? You'll have to see how we can incorporate within this framework. Okay, so again, so to repeat, I mean, deblurring is something that we have not looked at yet. The forward problem of image blurring we have seen, but then deblurring we have not seen. So the deblurring is like given a blurred image, estimate the focused image, okay, of the scene. Then there is something called image super resolution. Okay, image super resolution. All these. So in this case, right, when you talk about a degradation, the degradation in this case is blur. When you talk about image deblurring, so the original degradation is blur and probably noise. It's blur plus probably some noise, right, which can be AWGN typically. Image super resolution here, right, this is because of poor sensor resolution. Okay, so degradation in this case is really a sensor resolution. And when we say super resolution, we really mean spatial super resolution. There is also something called temporal super resolution and so on, but then we limit ourselves to spatial super resolution. So it's like saying that I give you an image which is of a low quality. That means you have, let's say, m cross m pixels, okay, and then I want you to produce something which is like alpha times m, okay, where let's say alpha, okay, could be like 2, 3, whatever. You want to go up by a factor. So it's like saying that I have a low resolution sensor here. Let's call this LR, and then I want to take this image and be able to produce a high resolution image out of it. This is again an ill-posed problem, okay? Because it's easy to get given a high resolution image. Getting the low resolution image is straightforward, but then given a low resolution image, when you try to solve the inverse problem to acquire a high resolution, to sort of produce or estimate a high resolution image, that is an ill-posed problem. Remember, this is not the same as to say interpolating an image, because interpolation does not introduce anything new, whereas super resolution is supposed to recover the original image. Okay, so here you are supposed to recover the original high resolution image, okay, which of course you are not able to see the original high resolution image. Okay, you are not able to see this image, of course, right? All that you can see is this low resolution version of that, which we call as LR. So you can think of this as a cell phone kind of, a poor cell phone, and this could be a high-end cell phone. So what you're sort of saying is that I would like to capture because if it's a cheap cell phone, it costs me less. Therefore, I'll actually I will capture a low quality image, but then I'll use some signal processing algorithm which will then tell me which will then kind of give me the equivalent of what I would have otherwise captured with a high-end phone. So if you take this LR, it will produce an HR as though the HR was captured from a high-resolution phone, in the sense that it saves me a lot of money. Right? So the idea is that these are two problems that we will definitely be looking at, okay, in more detail. And then again, there are several things that come under this kind of restoration umbrella. These are not the only two problems. Sometimes, right, people talk about image dehazing. Okay, before going there, right, let me also talk about what is called image synthesis problem, which is again closely related to a deblurring problem. So in image synthesis, right, so one of the areas where image synthesis is very important is what is called optical microlithography. Okay, it's called optical microlithography. And here the idea is that you want to be able to estimate a mask. Okay, so let's say, right, this is a mask, this is an optical mask that you want to be able to estimate, that you want to find out what should be that optical. Again, it's an inverse problem. There is an optical mask that you would like to estimate such that when it goes through an optical imaging system, okay, so optical imaging system, it goes through an optical imaging system in order to be able to produce some kind of a print on a silicon wafer. So I want to produce a pattern on a wafer, right? So here is a silicon wafer, and you want to find out what should be the mask such that when it is passed through an imaging system, it produces a desired, okay, so this is a desired pattern on the mask, a desired pattern on the wafer, okay. Now, right, you know exactly what you want in this case, which will be a desired pattern. But then the thing is, right, you would not know what is the mask, right, which should be able to know, which I should be solving for, in order that when it is passed through an optical imaging system, whose characteristics I might know, I would see this kind of, this kind of a desired pattern. Then, okay, so in a sense, this is called the synthesis problem. We're trying to synthesize a mask, an optical mask, such that, right, it gives me a certain output, a desired output. Now, furthermore, right, you can go on and then you can talk about even, let's say, something like image dehazing. Okay, now, right, we know that haze will haze typically leads to a poor contrast in the image, right? Whenever you see a picture that is affected by fog, haze, and so on, right? That's such pictures look actually very hazy. So in the sense that, they seem to have lost contrast. And therefore, right, the idea is that dehazing would, of course, be able to remove the contrast and be able to give you back the original image. Now, if you look at the contrast stretching problem that we saw earlier, which was using histogram and all, that was more an image enhancement kind of an idea. Now, here, right, this is more objective in the sense that you again use, in this case, you use the physics of image formation, in the sense that, right, you might say that my observed image g of x comes as some, let's say, t of x into, let's say, I of x, okay, instead of I of x, let me say f of x, okay, plus, let me say, 1 minus t of x, okay, into a. Okay, now this is the model. This is the model for haze. Now f of x is your original clean image, okay, which is what you would have liked to see. Okay, this is your clean image, which you would like to see. Unfortunately, you don't see f. You would rather what you end up seeing is this hazy image. This is the hazy observation. Okay, so and then t of x is called really a transmission map. Okay, this is called a transmission map. Okay, in the sense that this is typically, right, given as e raised to minus beta times d of x, where beta kind of represents attenuation. This is an attenuation factor. This could also be a function of the wavelength. Okay, if it is underwater, it can be a function of wavelength and so on. D of x is really the distance of the scene point from camera, of the scene point, right? And A is called the air light. Okay, so air light. Okay, so the idea is that ideally you would have liked to see f, but then what you see is really kind of a convex sort of a combination, right, of these two terms. And this kind of a convex combination leads you to an image that looks hazy. And the idea is that can you solve for the transmission map, whatever, right? I mean, so what is known to you is only g of x, and you're asking what is then the original clean image. It's like saying that how would the scene look like if it was captured on a day, right, when there was no haze. So therefore, right, f of x is like really a clean image that you would have otherwise seen. But then, right, you're not able to see that. So when somebody gives you f, somebody gives you t, somebody gives you air light, you solve for g, that is a forward problem. Now, when somebody gives you g and say solve for f, that is the inverse problem. So dehazing is again an inverse problem. Similarly, right, people have done what is called image deraining. Okay, again, right, this is another kind of problem where, let's say, I have a picture that is actually affected by raindrops. So I take a camera outside when it is raining, and then I capture a picture, and the point is because of the raindrops, right, I see an image which is affected by rain droplets. And therefore, right, I would like to ask, can you sort of give me back an image such that it is rain-free? Okay, so basically produce a rain-free image. So here, degradation is really the rain, okay, and produce a rain-free image. And therefore, right, you would like to undo its effect in order to be able to produce a rain-free image. Okay, and this list kind of, right, will go on. Okay, I mean, and then there is something called rolling shutter correction, which I mentioned to you right in the beginning. Okay, rolling shutter is again an effect of motion of the camera. Right, I mean, especially when you have a shutter mechanism that is rolling shutter, which is kind of a correction that you need to do in order to account for the camera motion effects, and this kind of a geometric correction. Okay, so here, here what kind of correction that you want to do. Okay, so this kind of a degradation is really a geometric degradation which you would like to do a correction for. So this is a geometric correction. Then I can also tell you maybe, right, some more. What is that? Well, I told you about super resolution descaling. Okay, and so on. Okay, rolling shutter, and then you can high dynamic range imaging and so on. Right? I mean, there are so many of them. It's called high dynamic range imaging and so on. Okay, etc. In fact, I just wanted to mention that this is a deblurring thing, right? That I mentioned in the earlier slide. A deblurring. This is still used very heavily by the astronomic imaging folks. Astronomical imaging. Okay, this is used very heavily, and of course, this is something that we would also like to have in our own cameras and so on, right? So deblurring could also mean optical blur, motion blur, and so on. Therefore, right, deblurring is again something that is very relevant, right? Even as I speak, right? Even with respect to your own cell phones and so on. Okay. By the way, this tx is 0 less than or equal to tx less than or equal to 1. Okay. Now, okay. With that said, right? I mean, let me just show you a few examples of these, so that you get an idea about what I'm actually what we're trying to do really. Okay, now let me just pull this up. Restoration, right? Okay, now before restoration, let me talk about the synthesis problem, right, which I said is for optical microlithography. If I show you that, then we will see this. Okay, so we made synthesis. Let me first show you that. So if you see here, right? I mean, so if you see this image, okay, what you really find is, okay, what you actually find, okay, find is that, right? You would like to, so the whole idea is, right, is to be able to produce a mask such that the output looks sharp, right? Such that the binary wafer, okay, so the binary pattern that you actually print on the wafer is actually sharp. Okay. Now, if you see this example, right, if you try to take a mask that is already sharp, the idea is that the binary pattern should emerge like this on the wafer. But then if you think that the original mask should also be of the same shape as your final output, then what happens is when it goes through the optical process, right, all these corners become rounded. Okay, which means that the binary pattern that you end up seeing, right, is not sharp like the one that is in the mask. Therefore, one would like to ask, what should be the mask like so that the output looks as sharp as this? Then if you solve this problem, right, as an inverse problem, it turns out that the mask ought to be like this, which is not at all easy to sort of, right, imagine. And I mean, if you were to just sit back and think about what might be that mask that would lead to a pattern that is really sharp at the corners, you and I, right, just like that, if you were to sit back and think about what might be the mask, you would never have been able to arrive right at this answer. I mean, right? I mean, it looks like you need a small little flower pattern at all the corners, right? This is not something that we can automatically do. Right, so in that sense, I wanted to clearly understand that restoration is a more objective way. Right? It is not about just visual appeal or something. This is about understanding what is the forward process, and therefore, right, if that is causing some kind of a degradation, then you want to be able to invert it or undo it. Okay, so in this case, the image synthesis problem turns out that the mask should be like this in order for the binary pattern to be sharp at the corners. Okay, this is the synthesis problem that I mentioned. Then, as I said, there are also other problems with regards to restoration. So here are some examples that I'm sure you will like. Okay, so the first example, let me show you, is about dehazing and deblurring. So, for example, some of these factors, right, could also occur together. Okay, it doesn't have to be just dehazing alone or deblurring alone. So, in this case, you see an aerial image, so it is affected by haze as well as blur. And therefore, right, when you actually solve it as a kind of a restoration problem, the deblurring and dehazing problem, what you find is this image, right? So in this image, clearly you can see that it is kind of haze free, and it is also more sharp because we have also been able to solve for remove the blur. Okay, which is of course in this case a kind of a motion blur. Now moving on, okay, you can also have high dynamic range imaging. Okay, and then here is, you see, underwater kind of de-skewing. So whatever I said till now were all for surface images. Now you can also see that right, if you, okay, now let me just play this video, okay, and so it's like this. So if I drop a stone, right, in water, okay, what you would see is this. Okay, what you would see as a pattern, right, is this. Let me just play that video for you. Okay, so if you play this video, okay, you'll be able to see that you'll be able to see this water, right? So as you drop a water, so right, this is an image taken inside an aquarium, and we dropped, and then at the bottom, right, we kept an eye chart, and you can see that all these letters and all, right, become skewed, and you would like to see the image without any skew. This is again a restoration problem, and if you solve for it, right, without accounting for it, you won't be able to get a kind of a good picture. Whereas if you actually account for it, then all these letters will all get straightened up. But if you see here, right, they're all skewed. Okay, this is called really a de-skewing problem, right, and so on. Okay, and therefore, and the idea is that, right, the idea is that there are so many of these problems, right, that come under a restoration. Here is another. Okay, this is about another kind of dehazing. Okay, so here you have a hazy image, and then here you have a dehazed image. Now, if you see here, right, this is an underwater image. Okay, so the early underwater that I showed you was for de-skewing. This for actually doing really what is called a color correction. A color correction in the sense that if you see this image, this is an underwater image, and therefore it has a lot of greenish tinge. Right, simply because underwater, in underwater, the red wavelength is the one that gets attenuated the most. The green and blue kind of survive. Right, and therefore, you see a big greenish tinge in this image. Whereas, so the idea is that you would like to do a color correction such that you can actually retrieve these components. You like to retrieve the RGB components, right, as you would have seen otherwise on the surface. So if you solve for such a color correction, right, then you can actually find this image out. Okay, again, this comes under restoration framework. Okay, so you understand what kind of a degradation occurs in the forward process. Right, what these transmission coefficients are, how they kind of depend on their wavelength. So in that equation that I wrote for haze, there was a beta, which is said is an attenuation coefficient. So in this case, an underwater beta becomes a function of wavelength, and therefore, right, you need to use that fact in order to be able to solve for the original clean image. All right, so I hope right, you get an idea about deblurring and all of that, and then deblurring, deraining, and then of course I couldn't show you derain example, but I've shown you examples of dehazing, right, and hydrodynamic range imaging, de-skewing, and so on. Okay, so see, moving on, we would like to focus, right? We'd like to focus our efforts on these two problems. Okay, we'd like to look at image deblurring in particular, and then follow it up with some ideas about how to do image super resolution. Okay, and the idea is that, right, if you can understand these two problems, then all that would change as you hop from one problem to another is the kind of observation model that you have. But then most of the ideas, right, otherwise the general mathematics and all that follows is going to be somewhat similar. Okay, I mean, I'm not saying they're all identical and so on, but a lot of ideas that we talk about in terms of optimization, right, in terms of right, uniqueness, existence, ill condition, all those things will come up, right, in a sort of uniform way across these problems, and therefore, right, even if you understand one or two problems well, right, it is enough. One does not have to kind of go through each one of these individually in order to understand the framework as such. Okay, what do we mean by image deblurring? Okay, and right, I'm going to show you that inverse problems are not easy to kind of deal with. The forward problem, like I said, is easy, right? If I give you an image and then ask you to blur it, you know to kind of blur it. That's a forward problem that is straightforward. But an image deblurring is typically not straightforward. Even if you assume the simplest of situations, such as AWGN noise, space invariant blur, blurring known, all of that, even then, right, this turns out to be a hard problem to solve. Okay, but then, right, along the way, right, we will see how we can actually handle this kind of a difficult issue. Now, the way we kind of model, right, as we all know, okay, what do we say? We say that F is the original image. Okay, this is unknown. Okay, this is not something that we can see. Okay, this is the unknown. Okay, this is what we want to solve for. What happens? It goes through an H, which could be a PSF, a point spread function, and then something gets added to this. Let's say that I've got noise that gets added to this, and then you get your G. Okay, so G is, let's say, HF plus N, right? Where this H contains the impulse response is its entries. Zero is an impulse response, right? Impulse response entries, and what you want is really, right? So what you know is only G. Okay, we don't see F. And maybe, right, we might know H, okay? And in some cases, we may not even know H. The problem is, given this observation, okay, this is really a blurred observation. Blurred, so in this case, it's blurred and noisy, right? Blurred and noisy observation. So, the idea is that given this guy, right, what kind of a processing will you do, right? What kind of processing, let's say, let's call this a restoration. Let's call this a filter, a restoration filter. What kind of a restoration filter will you apply on G in order to be able to get back F? I wouldn't say you will get F back, we'll write F hat. Okay, so that right, we understand that F hat is something that's going to be close to F, hopefully. Okay, now this is a deblurring framework. Okay, this is the forward problem, this is the inverse problem. Okay, this is forward, okay, and this is the inverse. Okay, and we would like to solve this problem. Now, the whole idea behind restoration is that, right, we like to know how much of the model we know. Okay, in most cases we know the physics of the image formation, what was leading to this degradation, and so on. And therefore, right, in this case we might know whether it is space invariant blur or space variant blur. Right, accordingly, right, we would know whether to use a space invariant etch or a space variant etch, and so on. Similarly, noise, we might know that it is additive, and then it could be AWGN, a Gaussian kind of noise. All these are things that we might know. In addition, right, we might also assume that that the input to this filter could go in the form of knowledge of F itself, right? But this knowledge of F, it doesn't mean that I know all of F. Some kind of a generic knowledge of F, what we call as really a prior. Okay, and this prior and all is needed whenever you try to solve an inverse problem. It encounters issues of numerical stability. Right, and in order to overcome this numerical stability issue, it is imperative that we supply, right, to this filter, to this restoration filter, as much know-how as we have about F, about noise, about H, whatever we know. For example, even H, for example, impulse response, we might either know it completely, or let's say that we might have some clue about whether it is a motion blur or optical blur, whether it is sparse or isotropic. So all this information will all then be some kind of a prior. Then again, noise, right? We might know something about noise. Do we know its variance? Do we know that it is zero mean, right? Those kinds of statistics. So the entire block. Right? So here, right? So when I write prior, right, I could be prior about F, prior about H, prior about N, and prior about F. The interesting thing is even giving a generic prior about F. Something as simple as, suppose you ask, right, what could be a generic prior? You simply say that local intensity should look similar. That would be a generic prior. The Markovian kind of a prior, right, which we have seen before. Something as simple as that. Something, right, which is something that holds true across all images. It doesn't have to be just a face image or something, right? It would occur across natural images and so on. Simply adding a prior like that can stabilize your solution a lot. Because without these priors, right, any attempt to solve this kind of an inverse problem will lead to an F hat that can be very noisy. Okay, we'll see all of this as we go along, and therefore, right, one tries to regularize the solution. Okay, regularization is again something, okay, which we'll see along the way. So one tries to regularize the solution in the sense that we want to give more and more information about F, so the algorithm that is trying to solve for F, right, we can actually guide it towards a solution that is more sensible than some kind of a solution which is extremely noisy. Okay, now when we talk about really, deblurring, okay, when H is known, okay, if H is completely known, in some cases it may be possible to know H completely, we call it a non-blind deblurring problem. Okay, and when H is not known, H is unknown, we call it blind deblurring. Okay, we call it blind deblurring. So in this course, right, we'll only be doing NBD, which is non-blind deblurring. We'll assume that we know H. Okay, maybe I'll drop a hint along the way as to how do you solve a blind deblurring problem. But really, our focus will be on the situation when I know H completely and then I want to solve for F. Even this is going to be hard, and of course another assumption that we are going to make is we have a space invariant blur. Okay, because even this you will understand, you'll realize, right, is not easy at all, and it would require a lot of effort to even solve a simple problem like this.